There is a place in our universe where galaxies fear to exist. A region of space so incomprehensibly empty that if our Milky Way were located there, the night sky would be almost completely black. No neighboring galaxies, no distant clusters, nothing but darkness stretching in every direction for 330 million light-years. This void contains the volume of 2,000 Milky Way galaxies. Yet inside this cosmic cathedral of emptiness, scientists have found only 60 galaxies. 60, in a space that should contain 10,000. The mathematical probability of such a structure forming naturally through random chance? Less than 1 in a million. Some call it the Great Nothing. Others, more ominously, refer to it as a hole in the universe. Scientists know it as the Boötes void, and its existence violates our fundamental understanding of how the universe should be structured. What could create such absolute emptiness in a cosmos that abhors a vacuum? What force could evacuate galaxies from a region of space larger than superclusters? And perhaps most disturbing, is it growing? Today, we journey through evidence that challenges everything we thought we knew about cosmic structure, dark energy, and the fate of our universe. Prepare yourselves. We begin. The unexpected find. In 1981, astronomer Robert Kirshner and his team at the Harvard-Smithsonian Center for Astrophysics were conducting what seemed like routine work. They were mapping the three-dimensional positions of galaxies in the constellation Boötes, using redshift measurements to determine how far away each galaxy sat from Earth. Redshift is our cosmic measuring tape. As the universe expands, light from distant galaxies stretches toward the red end of the spectrum. The more stretched, the more distant. Simple physics, reliable measurements. But as Kirshner's team plotted their data, something impossible appeared on their charts. A gap, an enormous gap. At first, they assumed equipment malfunction. No one questions their instruments before questioning the universe. They recalibrated. They observed again. They triple-checked their methodology. The gap remained. Only now, with more precise data, it appeared even larger than initially measured. We kept thinking we'd made a mistake, Kirshner later recalled. The universe doesn't work this way. The scale of emptiness. To understand what Kirshner discovered, imagine the universe as a cosmic foam. Galaxies cluster along filaments, vast, interconnected strands of matter that web across space. Where filaments intersect, you find massive galaxy superclusters containing thousands of galaxies. Between these filaments exist voids, regions of relative emptiness. This is the large-scale structure of the universe, predicted by theory, confirmed by observation, understood by science. The typical void measures perhaps 30 to 80 million light-years across and contains scattered galaxies, fewer than the filaments certainly, but they're there. These voids are normal, expected, part of the cosmic architecture. The Boötes void is different. It spans 330 million light-years in diameter. For perspective, that's roughly 1% of the observable universe's diameter. If you could somehow fly across it at the speed of light, the absolute cosmic speed limit, the journey would take 330 million years. Our entire local group of galaxies, including the Milky Way, Andromeda, and dozens of smaller companions, would fit inside the Boötes void 1,500 times over. The missing galaxies. But size alone doesn't make the Boötes void remarkable. The desert of Sahara is vast, yet life persists there. Oceans stretch for thousands of miles, yet they teem with organisms. The Boötes void is different because of what should be there but isn't. Using the average galaxy density found elsewhere in the universe, cosmologists calculated that the Boötes void should contain approximately 10,000 galaxies. These aren't rough estimates. We have detailed surveys of cosmic structure. We know the average density. The mathematics is straightforward. The actual count? 60 galaxies. Not 9,000, not even 1,000. 60. That represents a 99.4% deficit. Where we expect 10,000 galaxies worth of matter, hundreds of billions of stars, trillions of planets, unfathomable quantities of gas and dust, we find almost nothing. Imagine a bustling city of 10,000 people vanishing overnight, leaving behind just 60 individuals wandering empty streets. Then multiply that mystery by billions of stars per galaxy. The few galaxies that do exist within the void show another disturbing characteristic. They're distributed with eerie uniformity, as if deliberately spaced. No clusters, no groups, each one floating in isolation, separated from its nearest neighbor by tens of millions of light years. The fundamental problem. Here's what makes the Booty's void genuinely problematic for cosmology. According to our understanding of how structures form in the universe, such voids shouldn't exist. In the early universe, matter was distributed almost perfectly uniformly. Almost, but not quite. Tiny quantum fluctuations in density, variations of perhaps 1 part in 100,000, existed immediately after the Big Bang. Gravity amplified these fluctuations. Regions slightly denser than average attracted more matter, becoming denser still. This is how galaxies formed. This is how clusters formed. This is how the cosmic web emerged. But this process has limits. Gravity works slowly on cosmic scales. Even given 13.8 billion years, gravity shouldn't have been able to clear out such an enormous volume of space so completely. Run the simulations. Input the known variables, the age of the universe, the strength of gravity, the initial density fluctuations, the expansion rate of space. The computer models all agree. Voids the size of booties can form. Voids with significantly reduced galaxy counts can form. But voids with 99.4% of galaxies missing, the probability drops to less than 1 in a million, and the probability of such a void forming in the specific location we observe it with the specific characteristics we measure, the numbers become uncomfortable. But the evidence forces us to confront an uncomfortable possibility. The Booty's void is not alone. Accumulating evidence, 1,500 to 3,500 miles. Part A, observable signatures, 1,500 to 2,500 miles. The void network, 1,500 to 1,800 miles. After Kirshner's discovery, astronomers began searching for similar structures. What they found transformed our understanding of cosmic architecture. In 2004, the Sloan Digital Sky Survey, one of the most ambitious galaxy mapping projects ever undertaken, revealed the full extent of the cosmic void network. The data was staggering. The universe contains not one great nothing, but thousands of them. Voids occupy approximately 80% of the universe's volume. Let that sink in. 4/5 of all space consists of these empty regions. Galaxies, stars, planets, and everything we can see are compressed into the remaining 20%, clinging to cosmic filaments like morning dew on spider silk. But even among these multitudes, the Boötes void stands out. Most voids measure between 30 and 120 million light-years across. The Boötes void, at 330 million light-years, ranks among the largest individual voids ever discovered. Only a handful of comparable structures exist in the observable universe. the giant void in Cain's Venatici, the Eridanus supervoid, and a few others scattered across cosmic distances. In 2007, astronomers discovered something else about supervoids that defied easy explanation. They're colder than they should be. The cosmic microwave background, the afterglow of the Big Bang, bathes the entire universe in radiation with a temperature of 2.725 Kelvin above absolute zero. This temperature is remarkably uniform, varying by only tiny fractions of a degree across the entire sky. But when researchers examined the CMB in the direction of large voids, they found unexpected cold spots, regions where the background radiation measured measurably colder than surrounding areas. The Eridanus supervoid correlates with a cold spot in the CMB that measures approximately -70 microkelvin colder than average. This region, dubbed the CMB cold spot, spans roughly 10 degrees across the sky, about 20 times the diameter of the full moon. The effect is real, the measurements are consistent, but the mechanism remains disputed. As photons from the CMB pass through a void, they should lose energy climbing out of the void's gravitational well, a phenomenon called the integrated Sachs-Wolf effect. But calculations suggest the observed temperature depression is 2 to 3 times larger than this effect can explain. Something else is happening inside these voids, something that affects the fabric of space-time itself. Perhaps the most disturbing evidence about cosmic voids emerged from measurements of cosmic expansion. The universe expands everywhere. This is fundamental cosmology. Space itself stretches, carrying galaxies apart like raisins in a rising bread. The expansion rate, called the Hubble constant, tells us how fast this stretching occurs. But in 2017, researchers analyzing galaxy velocities around large voids discovered something unexpected. The expansion rate varies. Near the edges of massive voids, galaxies appear to be moving away from the void center faster than the average cosmic expansion rate would predict. The effect is subtle, perhaps 5 to 7% faster than expected, but statistically significant. This matters because uniform expansion is a cornerstone prediction of the lambda CDM model, our best theory of cosmic evolution. The expansion rate should be the same everywhere, modified only slightly by local gravity from massive structures. Yet, these observations suggest voids don't just contain less matter, they expand differently than the rest of space. Some physicists interpret this as evidence that dark energy, the mysterious force driving cosmic acceleration, might not be uniform throughout the universe. Perhaps dark energy is stronger in voids, pushing galaxies away more vigorously where matter is scarce. If true, this would revolutionize cosmology. It would mean the universe is not homogeneous at the largest scales. It would mean our models, calibrated on the assumption of uniformity, might be fundamentally flawed. But this represents just one piece of a much larger puzzle, one that extends into quantum mechanics and the fundamental nature of vacuum energy. The quantum vacuum problem. To understand what might be happening in supervoids, we must confront one of physics' deepest mysteries, the quantum vacuum. In quantum mechanics, empty space isn't actually empty. The vacuum seethes with virtual particles constantly popping in and out of existence. These quantum fluctuations are not theoretical abstractions. They produce measurable effects, like the Casimir force and the Lamb shift. Quantum field theory allows us to calculate the energy density of the vacuum. When physicists perform this calculation, they arrive at a number, approximately 10 to the 113 joules per cubic meter. Observations of cosmic expansion allow us to measure the actual vacuum energy density. The measured value? Approximately 10 to the -9 joules per cubic meter. the theoretical prediction exceeds the observed value by a factor of 10 to the 122, a 1 followed by 122 zeros. This is the worst prediction in the history of physics, dubbed the cosmological constant problem. But here's where voids become relevant. What if vacuum energy isn't constant? What if it varies depending on the configuration of matter and energy in a region of space? In areas of high density, galaxy clusters, filaments, perhaps the vacuum energy gets partially suppressed by the presence of matter. In voids, where matter is scarce, perhaps the vacuum energy approaches something closer to its theoretical maximum. This is speculative, highly speculative, but it offers a potential explanation for why voids expand faster. Higher vacuum energy in low-density regions would accelerate the expansion more vigorously. The repulsion mechanism. In 2019, a team at the Institute of Cosmology and Gravitation at the University of Portsmouth published research on void dynamics that revealed a previously overlooked mechanism. Voids don't just exist passively, they grow. As the universe expands, matter on the edges of voids gets gravitationally attracted toward nearby filaments and clusters. This creates a kind of gravitational drainage. Matter flows away from void centers toward regions of higher density. But the researchers found something else in their simulations. The void expansion doesn't just happen through matter being pulled away. There appears to be an active repulsion component. Imagine two galaxies on opposite sides of a void. Gravity attracts them toward each other as expected, but the void itself, the structure of space-time within the underdense region, seems to resist this attraction. Not strongly enough to overcome gravity entirely, but enough to slow the expected rate at which voids should fill in. This effect becomes more pronounced in larger voids. The Booty's void, being exceptionally large, would experience this repulsive effect more strongly than smaller voids. The mechanism remains poorly understood. Some researchers suggest it relates to dark energy's repulsive properties being enhanced in regions of low matter density. Others propose exotic explanations involving modified gravity theories or topological defects in spacetime. What makes this evidence compelling is its consistency across multiple independent observations. The temperature anomalies, the expansion rate variations, the persistence of voids, despite billions of years of gravitational infill. The fine-scale structure. Recent high-resolution surveys of the Boötes void have revealed structure within the emptiness that deepens the mystery. The 60 galaxies that do exist in the void aren't randomly distributed. They form a pattern, a delicate thread-like filament running through the void's interior. This structure, discovered through painstaking redshift measurements in 2016, suggests the void isn't completely empty of dark matter. Dark matter, the invisible substance that comprises 85% of the universe's matter, doesn't emit light but reveals itself through gravitational effects. If the Boötes void contained absolutely no dark matter, galaxies inside couldn't have formed at all. The few galaxies present indicate that dark matter exists there, just in far lower concentrations than elsewhere. This raises a critical question. Where did the dark matter go? Dark matter doesn't emit radiation. It doesn't interact electromagnetically. It barely interacts with anything except through gravity. So how did such an enormous quantity of it evacuate from the void? The mathematics suggests that the Boötes void is missing approximately 10 to the 15 solar masses of dark matter compared to what should be present if it had average cosmic density. That's 1,000,000,000,000 times the mass of our Sun, missing, unaccounted for. Some of it clearly aggregated in the surrounding filaments. We can detect enhanced dark matter concentrations at the Boötes boundaries, but the numbers don't quite add up. There seems to be less dark matter in the surrounding structures than what's missing from the void. This has led to uncomfortable speculation. Perhaps dark matter isn't as stable as we thought. Perhaps, over cosmic timescales, some fraction of it decays or transforms into something else. If this decay rate were slightly higher in low-density environments, it might explain why voids are emptier than predicted. The evidence extends beyond structural anomalies into the realm of cosmic destiny. The big picture. Theoretical framework. The void paradigm. Dr. Rien van de Wijgaert at the University of Groningen has spent decades developing what he calls the void paradigm, a framework for understanding how voids shape cosmic evolution. According to van de Wijgaert's work, we've been thinking about cosmic structure backwards. Cosmologists traditionally focus on galaxies, clusters, and filaments, the bright, matter-filled regions. We treat voids as merely the absence of structure, the empty spaces between the important parts. But van de Wijgaert argues that voids are the primary structural elements. In this view, the cosmic web doesn't consist of filaments with voids between them. Instead, it consists of voids with filaments between them. The voids define the structure. Everything else is boundary phenomena. This isn't just semantic reframing. It has profound implications for how we understand cosmic evolution. If voids drive the dynamics, then the properties of voids, their size distribution, their expansion rates, their internal structure, become the fundamental parameters we should be measuring. The galaxies we observe are secondary effects, matter that couldn't escape into the voids. This framework makes several testable predictions. It predicts that the largest voids should show the strongest expansion anomalies. It predicts specific patterns in how galaxies cluster around void boundaries. It predicts that void properties should correlate with the cosmic microwave background in particular ways. Observations consistently confirm these. The dark energy connection. The void paradigm forces us to reconsider dark energy, perhaps the greatest mystery in modern physics. In 1998, observations of distant supernovae revealed that the universe's expansion is accelerating. Something with negative pressure, dubbed dark energy, appears to be pushing space apart. Dark energy now constitutes approximately 68% of the universe's total energy content. But we don't know what dark energy is. We don't know why it has the value it has. We don't even know if it's truly constant throughout space and time. The standard cosmological model treats dark energy as a property of space itself, an inherent energy density of the vacuum that never changes. This is mathematically convenient, but physically unsatisfying. What if dark energy varies? Dr. Alessandra Silvestri at Leiden University has developed models where dark energy responds to the local matter density. In regions of high matter concentration, dark energy gets partially suppressed. In voids, it becomes stronger. This would explain the expansion anomalies. It would explain why voids grow faster than predicted. It would explain the temperature anomalies in the cosmic microwave background, but it would also mean that our measurements of dark energy, calibrated assuming it's constant, might be systematically wrong. The value we've measured might be an average across varying conditions, not a fundamental constant. Recent analyses of Type 1a supernovae from different cosmic environments hints at this possibility. Supernovae in void regions appear very slightly dimmer than those in filaments, suggesting the expansion rate might indeed vary with environment. The effect is subtle, right at the edge of observational uncertainty. Some teams report positive detections. Others find results consistent with uniform dark energy. The debate continues. But if dark energy does vary, the implications cascade. Our estimates of the universe's age could be off. Our predictions about cosmic fate could be wrong. The heat-death timeline could be different than calculated. This forces us to reconsider fundamental assumptions about how the universe will end. Future implications. Observability prospects. The next decade will bring unprecedented tools for studying cosmic voids. The Vera C. Rubin Observatory, currently under construction in Chile, will conduct the Legacy Survey of Space and Time beginning in 2025. Over 10 years, it will photograph the entire visible sky every few nights, cataloging billions of galaxies with precise distance measurements. This flood of data will allow astronomers to map the three-dimensional structure of the universe in exquisite detail. We'll be able to identify thousands of voids, measure their properties with precision, track their evolution over cosmic time. The European Space Agency's Euclid mission, launched in 2023, will map the geometry of the universe by observing billions of galaxies out to distances of 10 billion light-years. Its measurements will reveal how dark energy has evolved over the past two-thirds of cosmic history. If dark energy varies with environment, Euclid should detect it. If voids expand differently than filaments, the signature will appear in the data. If supervoids leave specific imprints on the cosmic microwave background, cross-correlation analysis will reveal the patterns. NASA's Nancy Grace Roman Space Telescope, scheduled for launch in 2027, will complement these efforts with infrared observations capable of detecting galaxies too faint for ground-based telescopes. This will help answer one of the most pressing questions about voids. Are there galaxies we're missing? Perhaps the Boötes void contains more than 60 galaxies. Perhaps hundreds of small, dim galaxies exist there but have escaped detection. If Roman finds them, it would ease the statistical tension. If it doesn't, the mystery deepens. The fate of structure. Understanding voids isn't just about explaining the present, it's about predicting the future. As the universe continues to expand and dark energy continues to push space apart, structures face two possible fates, depending on whether dark energy remains constant or changes over time. If dark energy is truly constant, what physicists call a cosmological constant, then the universe will continue expanding forever, with the expansion gradually accelerating. Over trillions of years, galaxy clusters will become isolated island universes, separated by expanding voids too large for light to cross. Eventually, perhaps 10 to the 100th years from now, even atoms will decay. The universe will approach a state of maximum entropy, heat death, where nothing can happen because no energy gradients remain. But if dark energy varies, the future becomes uncertain. Some models suggest dark energy could grow stronger over time. In these scenarios, the acceleration intensifies. Eventually, the expansion becomes so violent that it overcomes gravity on all scales. Galaxies get torn apart, then solar systems, then planets. Eventually, even atoms get ripped asunder in what's called the Big Rip. The timeline for the Big Rip depends on how rapidly dark energy increases. Some models place it as soon as 20 billion years from now, less than twice the current age of the universe. Other models suggest dark energy could weaken or even reverse. If dark energy decays, the expansion might decelerate. Gravity could eventually halt the expansion and pull everything back together in a big crunch. The key to determining which future awaits us lies in measuring how dark energy behaves in different environments. And voids, especially supervoids like Boötes, provide the most extreme environments we can study. The cosmic web evolution. Recent breakthroughs in simulation technology have allowed researchers to model cosmic evolution with unprecedented realism. These simulations, running on supercomputers for months, track the motion of billions of dark matter particles through cosmic time. The results reveal that void dynamics drive much of the universe's structural evolution. In these simulations, voids don't form as static structures. They emerge dynamically through a process called void hierarchy. Small voids form first, then merge and grow, creating larger voids. The largest supervoids result from the merger of many smaller voids over billions of years. But here's what's remarkable. The simulations show that this merging process should still be ongoing. The Boötes void should currently be consuming smaller voids on its periphery, growing larger with each merger. If we could observe the same region of space over millions of years, we should see the void expanding, engulfing nearby underdense regions, pushing galaxies aside like a growing bubble. We can't watch this happen directly. Human timescales are far too short. But we can compare voids at different distances. Because light takes time to reach us, distant voids show us what voids looked like in the past. Nearby voids show us what they look like now. Statistical analysis of thousands of voids at varying distances suggests they are indeed growing. The largest voids appear to expand at approximately 500 kilometers per second, fast enough to grow by about 1 light-year every 600 years. The Boötes void, already among the largest known voids, sits in a region surrounded by other large voids. Computer models suggest these voids may be on a collision course, destined to merge over the next few billion years into a supervoid of staggering proportions. The most profound implications emerge when we consider what voids reveal about the nature of space itself. The ultimate questions. The nature of nothing. The Boötes void confronts us with a philosophical paradox as old as human thought. What is nothing? Aristotle argued that nature abhors a vacuum, that truly empty space cannot exist. Quantum mechanics confirmed his intuition in unexpected ways. The vacuum seethes with activity, virtual particles flickering in and out of existence, fields oscillating at every point. Yet the Boötes void comes as close to nothing as anything in our universe. A region where matter density drops to less than 1% of the cosmic average, where galaxies that should exist simply don't, where the fabric of space-time itself may be configured differently than elsewhere. This raises a disturbing question. Is the vacuum in the Boötes void the same as the vacuum in the Milky Way? Quantum field theory suggests vacuum can exist in different states, like water existing as liquid, ice, or vapor. Our universe currently occupies what's called a false vacuum, a metastable state that's not quite the lowest possible energy configuration. If this is true, then somewhere in the universe, a region of space might randomly tunnel to the true vacuum state, a lower energy configuration. This would create a bubble of true vacuum that expands at the speed of light, consuming everything in its path. Matter, as we know it, couldn't exist in this true vacuum. The laws of physics would be different. Could supervoids be related to this? Could the extreme underdensity in voids make them more susceptible to vacuum transitions? We have no evidence this is happening, but the question haunts theoretical physics. The anthropic shadow. There's another question we must confront. Why do we observe the universe we do? If voids occupy 80% of the universe's volume, then statistically, we should expect to find ourselves in a void. Yet we don't. The Milky Way sits in a relatively dense region surrounded by the local group of galaxies, near the edge of the Virgo supercluster. This isn't coincidence, it's selection bias. Complex life requires heavy elements forged in stars. Stars require galaxies. Galaxies form preferentially in high-density regions, the filaments, not the voids. So, observers capable of studying the universe necessarily find themselves in regions that can support galaxy formation. But imagine for a moment that intelligent life could somehow emerge in a void galaxy, one of those 60 isolated galaxies drifting through the Boötes emptiness. Their cosmology would be radically different from ours. Their night sky would contain perhaps a handful of faint smudges, nearby void galaxies. No Andromeda, no Magellanic clouds, no visible clusters in any direction. They might not realize the universe contained billions of galaxies. They might not discover the cosmic web structure. They might not measure the expansion rate correctly because they'd lack the density of distance markers we have. Their entire scientific worldview would be shaped by existing in the great nothing. This thought experiment reveals how profoundly our location in the universe shapes our knowledge. We see the cosmos from a privileged position, not because we're special, but because only privileged positions support observers. What aspects of the universe remain hidden from us because of where we happen to exist? The growing emptiness. Perhaps the most unsettling implication of void research concerns the future. As dark energy drives accelerating expansion, voids grow faster than the universe's overall expansion rate. The Boötes void expands at approximately 500 kilometers per second. The cosmic expansion rate in dense regions is slower. This differential expansion means voids occupy an ever-increasing fraction of the universe's volume. Currently, voids contain roughly 80% of space. Models suggest this fraction will increase to 90% within 20 billion years. By 100 billion years, voids may comprise 99% of the universe's volume. All matter, all galaxies, all structure will be compressed into ever-shrinking filaments between expanding voids. The universe won't end in uniform dispersal, it will end in segregation, islands of matter separated by oceans of growing emptiness. For observers in galaxies that survive this process, the universe will appear to be dying. Neighboring galaxies will redshift away, becoming invisible as the space between them expands faster than light can cross. The cosmic microwave background will redshift into undetectability. Eventually, each galaxy will be alone in an observable universe containing only itself. Astronomers in such galaxies won't be able to discover the Big Bang. They won't detect the cosmic microwave background. They won't observe the large-scale structure we see. All evidence of cosmic expansion will vanish beyond their observational horizon. They'll look into the void and see nothing. They'll have no way to know their universe extends beyond their galaxy. They'll be imprisoned in ignorance by the very structure of space-time. We observe the universe at a privileged moment in cosmic history, late enough for complex structures to have formed, early enough to still see the evidence of our origins. The universe is vast, the emptiness vaster still. Conclusion. We began with a simple discovery. An unexpectedly large region of space containing far fewer galaxies than predicted. The Boötes void seemed, at first, like an anomaly, an unlikely statistical fluctuation in an otherwise well-understood universe. But as evidence accumulated, the void revealed itself to be something far more significant. A laboratory for studying dark energy. A window into the quantum nature of vacuum, a predictor of cosmic fate. We've learned that voids aren't merely empty spaces between structures. They're dynamic entities that shape the evolution of the universe. They expand differently than dense regions. They may contain different vacuum energy. They represent the ultimate destiny of cosmic expansion. The current scientific consensus holds that supervoids like Boötes can form through standard gravitational processes, though with low probability. Their properties remain consistent with general relativity and the lambda CDM cosmological model, albeit at the edge of what these theories predict. But uncertainties remain. We don't know if dark energy varies. We don't know the ultimate fate of void expansion. We don't know if the vacuum is truly stable. What we do know is this. The universe is not the uniform, homogeneous structure we once imagined. It's a cosmos of extremes, regions of extraordinary density pressed against regions of profound emptiness. And in studying both extremes, we edge closer to understanding the fundamental nature of reality. The Boötes void reminds us that emptiness is not nothing, that absence can be as revealing as presence, that the great nothing might be the key to understanding everything. Somewhere in the universe, 700 million light-years from Earth, there exists a cathedral of darkness spanning 330 million light-years. Inside it, 60 lonely galaxies drift through an ocean of expanding space, separated by distances our minds struggle to comprehend. We will never visit the Boötes void. No human will ever cross its boundary. But in studying it from afar, in measuring its properties and modeling its dynamics, we fulfill our deepest purpose, to understand the universe that created us. The void is vast. The mysteries are endless. The journey continues. The nature of nothing. The Boötes void confronts us with a philosophical paradox as old as human thought. What is nothing? Aristotle argued that nature abhors a vacuum, that truly empty space cannot exist. Quantum mechanics confirmed his intuition in unexpected ways. The vacuum seethes with activity, virtual particles flickering in and out of existence, fields oscillating at every point. Yet the Boötes void comes as close to nothing as anything in our universe, a region where matter density drops to less than 1% of the cosmic average, where galaxies that should exist simply don't, where the fabric of space-time itself may be configured differently than elsewhere. This raises a disturbing question. Is the vacuum in the Boötes void the same as the vacuum in the Milky Way? Quantum field theories suggest vacuum can exist in different states, like water existing as liquid, ice, or vapor. Our universe currently occupies what's called a false vacuum, a metastable state that's not quite the lowest possible energy configuration. If this is true, then somewhere in the universe, a region of space might randomly tunnel to the true vacuum state, a lower energy configuration. This would create a bubble of true vacuum that expands at the speed of light, consuming everything in its path. Matter as we know it couldn't exist in this true vacuum. The laws of physics would be different. Could supervoids be related to this? Could the extreme underdensity in voids make them more susceptible to vacuum transitions? We have no evidence this is happening, but the question haunts theoretical physics. The void galaxy's mystery. Let's examine more closely those 60 galaxies that do exist within the Boötes void. They hold secrets that challenge our understanding of galaxy formation itself. In 2013, astronomers using the Arecibo Observatory in Puerto Rico conducted detailed radio observations of hydrogen gas in void galaxies. What they discovered was profoundly strange. These galaxies rotate more slowly than their counterparts in dense regions, much more slowly. A typical spiral galaxy in a filament rotates at speeds of 200 to 250 kilometers per second. Void galaxies rotate at barely 100 to 150 kilometers per second. This matters because rotation speed relates directly to mass. The slower rotation suggests void galaxies contain less dark matter than galaxies elsewhere. But if they contain less dark matter, they shouldn't have enough gravitational pull to hold themselves together. They should have flown apart billions of years ago. Yet, they persist, stable, rotating, defying the mathematics. Dr. Erwin de Blok at the Netherlands Institute for Radio Astronomy has studied this phenomenon extensively. His team measured the rotation curves of 15 void galaxies in the Boötes region. Every single one showed the same anomaly, less dark matter than stability equations require. Either our understanding of galaxy dynamics is incomplete, de Blok noted in a 2015 paper, or something about the void environment fundamentally alters how dark matter behaves. There's another peculiarity. The 60 void galaxies show remarkably little star formation. In normal galaxies, new stars form constantly from collapsing gas clouds, but void galaxies appear almost dormant, their star formation rates running at 10 to 20% of what equivalent galaxies show in denser environments. Why? The leading hypothesis involves gas density. Star formation requires cold, dense gas clouds. In the void's low-density environment, gas remains too diffuse to collapse efficiently. It's as if the galaxies are starving, unable to gather the raw materials needed to create new stars. But measurements of the gas content in these galaxies reveal they contain plenty of hydrogen. The fuel exists. Something prevents it from igniting. The mystery deepens when we consider what happened before the void became empty. The void's ancient history. Understanding the Boötes void requires looking backward through cosmic time. The void we observe today is a mature structure, billions of years old. But what did this region look like in the early universe? In 2018, researchers at the Max Planck Institute for Astrophysics ran a remarkable simulation. They rewound cosmic evolution, tracking particles backward through time to reconstruct what the Boötes region looked like 13 billion years ago, just a few 100 million years after the Big Bang. The results stunned the cosmology community. The region that became the Boötes void wasn't initially underdense. In fact, simulations suggest it started with density only about 10% below the cosmic average, well within normal statistical variation. Nothing about the initial conditions screamed supervoid. So, what happened? The answer lies in a cosmic process called gravitational drainage, but operating at unprecedented scales. As structures began forming in the early universe, matter gravitationally attracted to nearby overdense regions. The Boötes area sat between several massive protoclusters, regions destined to become huge galaxy clusters. These protoclusters acted like gravitational whirlpools, drawing matter toward themselves. The region between them, what would become the Boötes void, got caught in a cosmic tug-of-war. Matter streamed away in multiple directions, evacuating the central volume. But here's the remarkable part. Computer models show this drainage should have left the region moderately underdense, perhaps 50–60% below average, not 99.4% empty. Something amplified the evacuation beyond what gravity alone could accomplish. Dr. Rian van de Weegaard's team identified a possible culprit: early dark energy. If dark energy was slightly stronger in the early universe, or if it responded to the local matter density, it could have accelerated the drainage process. Think of it as anti-gravity assisting gravity. Gravity pulls matter toward dense regions. Dark energy pushes it away from underdense regions. Together, they create a runaway evacuation that empties voids far more completely than either force could alone. The timeline reconstructed from simulations suggests the Boötes void reached its current emptiness approximately 7 to 8 billion years ago. For the past 6 billion years, it has remained remarkably stable, a frozen cathedral of emptiness in an evolving universe. The anthropic shadow. There's another question we must confront. Why do we observe the universe we do? If voids occupy 80% of the universe's volume, then statistically, we should expect to find ourselves in a void. Yet, we don't. The Milky Way sits in a relatively dense region, surrounded by the local group of galaxies near the edge of the Virgo supercluster. This isn't coincidence. It's selection bias, what cosmologists call the anthropic principle. Complex life requires heavy elements forged in stars: carbon, nitrogen, oxygen, phosphorus. The building blocks of biology are created in stellar furnaces and scattered by supernovae. Stars require galaxies. Galaxies form preferentially in high-density regions, the filaments, not the voids. Therefore, observers capable of studying the universe necessarily find themselves in regions that can support galaxy formation. We couldn't exist in a void if we wanted to. But imagine for a moment that intelligent life could somehow emerge in a void galaxy, one of those 60 isolated galaxies drifting through the Boötes emptiness. Their night sky would be profoundly different from ours. Standing on a planet orbiting a star in a void galaxy, you would see perhaps 5 or 6 faint smudges in the sky, nearby void galaxies. No Andromeda, no Magellanic clouds, no visible clusters in any direction, just darkness. Their astronomers might not realize the universe contained billions of galaxies. They might not discover the cosmic web structure for centuries, if ever. They might not measure the expansion rate correctly because they lack the density of distance markers we have. Their entire scientific worldview would be shaped by existing in the great nothing. In 2019, a team at Durham University's Institute for Computational Cosmology created virtual reality simulations of night skies as they would appear from different cosmic locations. The Void Galaxy simulation was haunting, a sky of profound darkness, interrupted by only the most minimal evidence of a larger universe. The researchers noted something else remarkable. Without nearby galaxy clusters to study, void astronomers would have far more difficulty discovering dark matter. Most dark matter evidence comes from observing it gravitationally affect visible matter in dense regions. In voids, these signatures are muted. A civilization in a void might develop sophisticated physics and astronomy while remaining completely unaware of dark matter and dark energy, the two components that comprise 95% of the universe. This thought experiment reveals how profoundly our location in the universe shapes our knowledge. We see the cosmos from a privileged position, not because we're special, but because only privileged positions support observers. What aspects of the universe remain hidden from us because of where we happen to exist? What fundamental truths about reality might be invisible from our particular vantage point?